Hi, today's notes are on 4.5D. We're going to finish up solving polynomials, but then we'll talk about 4.6 where we have irrational and complex conjugates. So let's do a quick review. If you're given a polynomial, you should always check for the following steps. So first off, are you given a factor, a root, a solution, a zero? It could also be an x-intercept, right? If you are, then you want to use synthetic division. And the remainder should be 0. If you're not given a factor, root, 0, or solution or x-intercept, or if you have something here, then the next step is to try factoring. Okay, so I'm going to write over here, these are all factoring. There are a few things that I want you to try first. The first thing you should always do is try a GCF. So divide all out the GCF on all terms. If you can divide everything by every term by something. If you can't do GCF, you try the next one. You do the trinomial, which is usually our x method. And we could have just numbers that multiply to c and add to b if a equals 1. Or you could have a times c and multiply to b, right? And the thing to note here is that your exponent on b must be half of your exponent on a. So if I have a x to the squared plus bx plus c, this first one has to be double that second one. Okay? If you're given 4 terms, the thing you should check for is factor by grouping. And then at this point, this is also called double GCF. And I forgot to mention there's one more that students often forget. You can also do difference of squares. Which is your a squared minus b squared. Or you could do a cubed plus or minus b cubed, right? Sum and difference of cubes. Okay. Now, if nothing is factorable and you can't make it work, where say like you factor by grouping and the two parentheses don't match, or there are no numbers that multiply to c and add to b, then you need to use the rational roots theorem. And then you use synthetic division. Okay, and you look for a remainder of 0. So let's try this. Ready? The first thing we should do here is find the solutions for the following polynomials. So I'm going to try double GCF because I see 4 terms. We'll see if it works. I know they can both be divided by x squared and x squared. They can both be divided by 3, 9 and 6. This one, I know it's going to be divided by a negative because there is a negative here. And let's do 4. Okay, so let's see if this works. 3x squared on the outside. What's left? 9 divided by 3 is 3. Take out 2 x's, I'll have 1 left. And then plus 2. Then I'll have negative 4. X minus, no, plus, oh sorry, not x. 12 divided by 4 is 3x. Plus 2. Okay, and in this case, let's set equal to 0. In this case, the two parentheses match, so I have 3x squared minus 4, and I have 3x plus 2 equal to 0. Okay, this is not a perfect square because there is no square root of 3, so we cannot continue factoring, and there's no GCF because they don't both have the same term. So I know this one is going to be 3x plus 2 equal to 0, right? So you could switch it and just say like you have 3x plus 2 equal to 0. If you want to skip that step and go straight to here, that's fine. We're going to divide by 3 on both sides, so we get x equals negative 2 over 3. I forgot to read the directions as to why we're doing this, so let's go back and highlight this. Find the solutions for the following polynomials. Okay, so I found one solution. Quick recap. Remember that if there is a degree of 3, there are 3 solutions. They could be repeated, they could not, right? They could be all unique, but in this case there will be 3 solutions. We found one of them. This next one, over here, we can solve, right? So I'm going to set 3x squared minus 4 equal to 0, and add 4 to both sides. I'm going to divide by 3 on both sides. And then I'm going to square root both sides. X equals, and this is where after I square root, please make sure you have your plus or minus, square root of 4 over 3. Well, I know the square root of 4 is 2, so I'll get 2 on the top. I don't know the square root of 3, so that stays as a radical in the bottom. But you cannot have radicals in the denominator, so I'm going to multiply by root 3 and root 3. This is called rationalizing the denominator. Okay, that means I'm going to have plus or minus 2 root 3 on top. And the reason we multiply by root 3 is because when we have root 3 times the root 3, that's really root 9, or square root of 9, which is 3. Okay, so these two square roots cancel each other out. And so I have 3 solutions because I have one negative solution here, and then I have one positive and one negative solution here. Let's try our second example. I'm going to check this again, GCF. Ooh, already I know this isn't going to work because 17 and 6, 17 is a prime number, right? So I can't divide by something, so it will never have the same numbers inside the parentheses. So factor by grouping does not work. We now have to use the rational roots theorem. Oh, it's a little rough because I know what the solution is. Now, on a test, if I give you a graphing calculator, you could list out all your possible solutions, right? I know it's going to be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6, because it has to have numbers that multiply to 6. Now, up until today, we had all real numbers, right? And they were all whole numbers, they were all rational numbers, like fractions, but take a look. We have an answer here that wouldn't have shown up if we had tried the rational roots theorem. This is what we call an irrational solution. So do you see how, like, if we tried the rational roots theorem here, it would have taken us a really long time to get to try a fraction. And so there would be, like, the factors of 8, like what multiplies to 8 and what multiplies to 9. 2 and 3 do multiply to 8 and 9, but we would have gone through all the whole numbers first with synthetic division before we got to this point, which is why you should always try factoring if possible. So in this case, I'm going to assume that there's going to be another set of messy numbers, just because if I gave you one of these, like, why not? But what we can do is check our graphing calculator. So I'm going to put here, graphing calculator. There are no leading coefficients, so luckily there's no fraction rational roots. But let's do a quick check. So I'm going to clear everything, and I'm going to set my window to standard zoom, so zoom 6. Okay, and I have nothing. And now I'm going to put in x to the third power plus 2x squared. I would follow along and just make sure you know how to do this. 17x plus 6. Okay, I'm going to go here and check it out. Okay, so there's a fraction there, and I think a whole number there, but I'm not sure. Let's check our table. So second graph will get you to table. Ooh, I don't like that I'm counting by decimals here. So I'm going to go to table set, second window, and instead of counting by 0.5, I'm going to start at 0, and I'm going to count by ones. Okay, so to get here, I said second table set. Doesn't change my graph, technically. I look at my table of values, I knew it was on the positive. There we go. So I have an x-intercept of 3. So now that I know that, I can jump into synthetic division with my x equals 3 and know that I should get a remainder of 0. Okay. So if I give you a graphing calculator, you could definitely do this and check it. Actually, you should. If I don't give you a graphing calculator, then you would have to try +1, -1, +2, -2, and then get to 3, which would really suck because it takes a while. So let's do synthetic division here. We know the remainder should be 0. Okay. And so our final, if we started with a cubed, our quotient will be a squared plus 5x minus 2. And this one comes down as x minus 3. Okay. I know my solution is going to be x equals 3 as one of them. I don't think there are numbers that multiply to 2 and add to 5. So since it's not factorable, I need to use the quadratic formula. Okay. Quick recap, just to make sure you're using the right formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so let's plug this in. Negative 5 plus or minus square root of 5 squared minus 4 times a is 1 and c is -2. Ooh, sorry, running out of space there. Shouldn't have bothered with that x equals, huh? All over 2 times 1. Okay, let's bump it over some. Negative 5 plus or minus 25 plus 8 all over 2. Okay, because -4 times -2 is +8. So that gives me negative 5 plus or minus square root 33 over 2. Now, if I could simplify that radical, please do simplify the radical, but since I can't, we're going to just keep going. And our second set of solutions is negative 5 over 2 plus or minus root 33 over 2. And since it's a positive and a negative and a third solution. Okay? So I'm going to have you guys try here. Please pause the video and try it. The second you try has a difference of cubes, so you want to factor this versus trying using synthetic division. This one, if you can use your graphing calculator to find a specific x-intercept first, right, or a 0, you can use that quickly to figure it out. I'm going to pause your video, and then we will go from there. Okay, so do a quick answer check. Hopefully these are the answers you got. And what you hopefully notice is that if I have a radical answer, right, or an irrational answer, there's always going to be a positive and a negative because our quadratic formula always has a plus or minus. So if I have a plus square root of b, and a and b are numbers, then I must have a minus square root of b as an answer as well. This is called the irrational conjugate theorem. Now, if I have a imaginary answer, the same thing happens because we have a plus or minus for imaginary numbers as well. So if a plus bi is an imaginary 0, then a minus bi must also be a 0. Okay? And if this is the case, then we can write some polynomial functions using this information down here, these complex conjugate theorems or the irrational conjugate theorem. So now here it says, write a polynomial function of least degree, that means don't do extra work, that has rational coefficients, okay, whole number or coefficients, and a leading coefficient of 2, and the zeros 2 and 3 plus square root of 7. Now that means 3 minus root 7 must also be a solution, okay? So my function, I'm going to have a leading coefficient of 2. One of my zeros is 2, so I'm going to have x minus 2. And then I'm going to have, this is the trickier part, you guys ready? X minus 3 And it actually doesn't matter what your signs are here, because I'm going to have 3 plus root 7 and 3 minus root 7. So this 3 has to change signs, but these two are going to switch regardless. So I'm going to have negative root 7 here and x minus 3 plus root 7. Okay, so be really careful. So I'm going to slide a paper under so it's easier for me to write. Be really careful that this 3, this positive 3 right here, okay, changes signs. So you never change it to plus and x plus, or x minus and x plus. Okay, they're both going to be negative. And now we need to multiply this out, which sort of sucks, okay, because let's say I wanted a polynomial function. We want rational coefficients, and these are not rational. So really what this means is multiply it out. So this is where my big X comes into play. And I'm never going to multiply the 2 to this part first. And I'm not going to do these two first, because something happens when we have conjugates, which is where we have a plus and a minus. So I'm going to set this up. And I'll have, let's see, x minus 3 minus root 7 and x minus 3 plus root 7. Okay, so let's fill these in. X squared, x times negative 3 is negative 3x, negative 3x, and negative times a negative is a positive 9. Okay, next what we'll have is 7 times x times negative 7, negative root 7. So I'm going to have negative x root 7. And then here I'll have positive x root 7. And the reason I didn't write it as root 7x is because that's hard to tell that it's outside. Okay, so I like flipping them just so that the whole number is in front. Do you notice that these two cancel out? And they should always cancel out, because if we have one negative, one positive, according to the the irrational conjugate theorem, we'll have one negative, one positive. And then over here, I'll have negative 3 times negative is a positive 3 root 7. And then here, we will have a negative 3 root 7. And these will also always cross out. I'll do double for that one. Okay. This one can't cross out. I have a negative times a positive, which is a negative. Square root 7 times square root 7 is 7. Okay, because 7 times 7 is 49, and the square root of 49 is 7. But that negative stays. And so for this part, we have x squared minus 6x, right, these two together, and then 9 minus 7 is plus 2. For this part right here, I can multiply that out and have 2x minus 4. Okay. Technically, this one has rational coefficients, so I could stop. If I wanted standard form, then you would have to keep going, right? So this one, let's just keep going and just have a final answer. I'll do it down here. (2x minus 4, x squared minus 6x plus 2, right? And you guys could multiply it out and get a final answer here. Okay. The same thing applies for complex numbers or complex solutions. So if I have x equals 0, this one has a leading coefficient of 1. X equals 5, x equals 1 plus I, then I know that 1 minus I is another solution. Okay. And so let's see, we have x minus 5, we have x minus 1 minus I, and x minus 1 plus I. And if you guys multiply this part out again, we know that this one, this one, this one, this one will cross out right away. Let's check it just to be sure. You guys ready? X minus 1 minus I, x minus 1 plus I. Okay. So this one will be x squared, negative 1x minus 1x, positive 1. I times negative I is negative I squared. You guys remember that I squared equals to negative 1. So this is going to be positive 1. Okay, so let's see. Negative ix, positive ix. You guys see that cancels? And then this will be negative, positive I and negative I. So those two also cancel. Okay. So then we have x squared minus 2x and then plus 2. And then x minus 5. And we can multiply that out, correct? Okay, so let me just show you a different way, because what if we get something like that? That is a hot mess. I don't really want to multiply fractions, right? And there must be a better way to get your a, b, and c value. So what if we recognize that this is similar to our quadratic formula answers? And so we know that we have negative b plus or minus b squared minus 4ac all over 2a. Now the problem is right now, that number down here is not multiplied by 2, right? So like 5 is not a multiple of 2. So could I then take everything and multiply by 2 on top and 2 on the bottom? Okay, so that gives me 2, and I know there's going to be a plus and a minus. Then there's going to be 2i root 14 all over 10. Okay, so now I know that 2 is negative b, so b must be equal to, let's see, we have a, b, and c. So b must be equal to negative 2, because a negative 2 becomes positive. A is equal to 10, so I'll write this here already. So let's set up our equation. You guys see that one? Okay, that's this and this. And then I know that 2a equals to 10. So a must equal to 5. And c, I'm going to set up using what I know left, which is this. Now this gets a little trickier because you can't just set b squared minus 4ac equal to 14. There's also a 2i. Okay, so really what this is saying is 2i root 14 equals to square root of b squared minus 4ac. Okay, and we don't want the square roots. So this one, in order to come out, had to be a 4 inside, right? Because the square root of 4 is 2. So really what this is saying is that I had a negative 4 times 14 inside. You guys okay with that? And when I simplify this, negative became an I, and the 2 squared is 4. So I know that my inside number, let's see, 4 times 14 is 56, equals to b squared minus 4ac. I know b and a already, so now I can solve. Okay, so b is negative 2 squared minus 4 times 5 times c. And now I can solve my equation here. I'm just going to write it up here. Uh-oh, did I mess up? Did I create a problem? No, I didn't. Okay, negative 60 equals to negative 20c. So that means c equals to 3. Okay, and that takes care of the plus and the minus here in one go. So this is sort of the same as multiplying it out, but we don't want to multiply with fraction radicals. So now I have, let's see, x minus 5. Sorry, I seem to really like 5. And then I have my a value, 5x squared minus 2x plus 3. And when I multiply this out, I can get standard form. Okay? I'm going to let you have fun with that because I think I'm done. You guys can multiply easily.
We'll practice in class. See you later.